Hi everyone, welcome to Data Talks Club, which is a community of people who love data. We have weekly events, and today we have one of such events. If you want to find out more about the events we have, there is a link in the description. Go there, click on that link, and you'll see everything we have in our pipeline. Do not forget to subscribe to our YouTube channel, very important. This way you will stay up to date with all awesome streams like we have today. And I really have to update this number because it's like 30 something K subscribers. So thanks everyone for subscribing to our YouTube channel. And then finally, we have a Slack community where you can hang out with other data enthusiasts. During today's presentation, you can ask any question you want. So there is a link in the description. There is a link in the live chat, sorry. Click on that link, ask your question, and then how do you prefer? Like, should we cover these questions as you go, or should we cover them at the end?
For me, it's fine. Also, in the meantime,
so I can interrupt you. So,
yeah.
So if the question is on topic to what you discuss right now, then I can interrupt you and ask the question. So yeah, please use Slido for asking questions, and I'll be keeping an eye on them, and we will be covering these questions. And right now I will stop sharing my screen, and now it's your turn.
Perfect. I'll share my screen now. Please let me know if it's visible.
Yes, it is visible.
Perfect. Let me this thing. Okay. Cool. Oops. Yep. Yeah. So hello everyone. I'm Sadik from Datamax, and today's talk will be about machine learning with array. How can we actually use GPU clusters with array, and how to get the best out of it with for our machine learning workflows. What I'm going to be doing today is first I'll talk a bit about why array, then we'll dig a bit deeper into array, its components, the native machine learning libraries that array provides, and then we will have a short demo about running model training pipeline in array, and we'll go through a bit about the UI provided by array. And then finally, we'll have a short summary. So first topic, why array? While researching about this talk, I discovered that array comes from the same lab that Spark came from in Berkeley, which is really interesting. And the researchers there had three main pillars why they decided to build array. This was around 2017, 2018. And first one was machine learning is pervasive in every domain. We have seen machine learning pop up in all sorts of domains, from bioinformatics, finance, generative AI, of course. But wherever there is people working, there is also machine learning involved. And this was one of the main incentives why people over there decided to build array to make machine learning as easy as possible for all sorts of domains. And the second part is distributed machine learning is a necessity. The reason for that is because we have seen that the amount of compute needed to build and to train machine learning models has been increasing logarithmically, while the compute power provided by CPUs has not been able to keep up.
Do you know where GPT-4 would go here?
I intentionally draw this red line a bit further away because there is no real number or no official number, but I'm pretty sure it might be way above in this graph.
Yeah, exactly.
And unfortunately, CPU power has not been able to keep up, even with if Moore's law were to keep true that the compute power would double every 18 months, it would still be lacking. And we have seen that this has not been able to keep up for so long. Of course, we have accelerators like GPUs and TPUs, but there is still a large gap between the compute power that such accelerators can provide and the compute power needed to train really good and big machine learning models. Therefore, there is no other way but to do distributed computing. And the third pillar is that distributed systems are hard. If you have been running your Spark cluster, or if you have tried to build a real system that is using multiple sorts of distributed computing components, you know that it is either too expensive because you need the people that really know how to glue things together, or you might end up having to use systems that are provided by certain cloud providers like Lambdas and all sorts of managed systems that any cloud provider can provide. But then you are bound to the availability of this cloud provider. If, for example, this cloud provider does not have the hardware that you need, then you cannot use it. Or if a system is not provided by this cloud provider, then you are not able to use it. And therefore, this brought to the researchers basically building Ray. And now that we know why Ray was built, now I wanted to say what Ray is. Ray is a general purpose library for distributed computing. It really tries to make it easy to use distributed computing in a very common way for developers. So if you are used to writing your Python functions, it should be easy to make these Python functions run in a distributed way. Ray also offers an ecosystem of native libraries to scale machine learning workflows. Basically, with Ray, you have a native way how to do the data processing, how to do model training, and how to serve these models. We will go through these libraries a bit later. And thirdly, Ray is built in a way that it runs everywhere. It can run in your local machine, it can run in Kubernetes, it can run in your bare metal machines, but also in any cloud provider. So now that we have a bit about why and what Ray is, I wanted to talk about the components that built Ray in order to make this thing come true. In the down layer here, you have the infrastructure, basically the hardware. It can be running on AWS, Azure, Google. It can be running your Kubernetes cluster or bare metal machines. And then on top of it, you have Ray Core, which is a universal framework for distributed computing. And this part offers you all the constructs that you need to have machine learning or to have any sorts of distributed application running there. They have things like tasks, which are basically functions, Python functions that are running in the cluster in a distributed way. There are things like actors, which would be classes or instances of classes that are running in the cluster. And then on top of it, you have the third layer, which would be more like the custom applications and the native libraries. Before, all these libraries were separate, but now they are all in under the same umbrella, Ray AI runtime, or Ray Air, it's called now. Basically, now you have the data, and this offers you the way how to process your data, and then Ray Train takes care of training your machine learning models. And Tune is very important when you are doing the hyperparameter tuning and trying to figure out the best hyperparameters for your algorithm, because you want to have the best model deployed. And then Serve takes care of serving the models, and RLib is a library for reinforcement learning. But you don't have to use all these runtimes in order to use Ray. You can also be building your custom applications, and then Ray would be able to support you to have the distributed computing just by using a simple construct in Ray. We will have a quick look about this in the demo later on, but also in the demo we'll be looking how to train MNIST model. Then, of course, just having the native libraries is also not enough. In order to be useful for most of the practical use cases, you need to have integrations, and Ray provides a lot of integrations for all sorts of tooling. You can be building, you can use the datasets library to your Dask data processing or Spark data processing, any sorts of integrations that you might have. For Ray Train, you can integrate with PyTorch, TensorFlow, also XGBoost and Horowod, and all sorts of tooling. And then here you can see basically any sorts of major Python frameworks is supported and integrated with Ray, but you can also contribute or build your own Ray integrations if something is not supported. And now I wanted to go a bit deeper into the architecture of Ray. So what makes it possible that you can run these sorts of massive parallel or massive distributed workloads in Ray? And from the first look of it, the architecture looks just like any distributed kind of framework. You have a worker process, and then you do have the kind of global control store that is some metadata, stores all the metadata about the cluster, all the information that you might need about where each task is running, information about the nodes that are there in the cluster, the hardware that they have available, and so on. You also have one driver process. This driver process can be running anywhere, but in this case, it's just running at the head node by convention. Also here below, we have the autoscaler. Autoscaler is a process that makes sure that you have the hardware that you need. If one of your tasks needs more resources than that they are available in the cluster, autoscaler will go ahead and start a new node and have this node join the cluster, but also the other way around. When the node is not needed anymore, or there is not enough workload in the cluster, then autoscaler will shut down this node and save you some money. But what is different for Ray from other distributed frameworks is this Raylet process. This Raylet runs in every node in the cluster, and it has two threads. One is the object store, and the second one is the scheduler. The scheduler is one of the main constructs in Ray that makes it scale effortlessly, because the decision here was that they don't want to have one single scheduler, but the scheduler should be distributed, and each node can decide autonomously if it wants to schedule the task or the job internally, or it wants to basically forward this task to another node that has, I don't know, free capacity or has more resources available. And the object store is some shared memory between all the nodes in Ray. What happens is each worker process would store their results or the output of or the input in object store, and then whenever this input or output is needed by other nodes or other processes, it will be accessible from object store. And ideally, array has the notion of data locality. So if one task has generated some output and stored it in the object store, one other task that will be using this output will tend to be scheduled on the same node where this data is. And therefore, we'll try to avoid having to copy data over. Also, the worker processes don't store data internally, but rather store everything in object store. And this makes it easy for data to be shared across tasks. Yeah, I think this was the hardest bit for me to understand about array. I don't know if there are any questions so far, Alexei.
Not specifically about that. There are questions, but we will talk about them at the end.
Wonderful. And now the next step is, how can I run my functions in array? And it's very easy to see that all you need to do is add this decorator array remote, and these tasks will be running in a distributed way. However, there are a few things to understand here. Whenever you want to run a function in an array cluster, you need to add this decorator.remote and then pass the input. That's all good. However, you will be getting a returned value immediately. And the returned value that you get is not actually the value of the computation, but it's a future. And having futures, similar to Scala futures, this allows you to continue executing the next instruction with the promise that you will be getting a response about the first instruction sometime in the future. And this allows array to be able to run multiple instructions and then start scheduling everything before actually having to return a response. And if you want to block the execution and actually get the response, you would have to use something like array get instruction, and then that's when array will stop, do the calculation, and then return you the output. And this is what translates into tasks in array cluster. We will see actually in the demo how tasks look like. And the actors that I mentioned in the beginning are basically classes, Python classes, and then for each instance of the class here, for example, we have C equals counter.remote. This will create an instance of this task, and this will be represented as an actor in our array cluster. And then you can run all these tasks on top of from this actor, and they would be all operating independently. So I think that's it about basically understanding what array is and how array works. And I'd like to jump into the demo.
Maybe if we do you think now it's time for questions, or you want to do them after the demo?
No, it's a good part here. We can.
Yeah. So maybe I'll just quickly share my screen so you can see the questions too. Let me see. So now I will stop sharing yours, because when I click share, it stops automatically sharing yours. So I'll take the first one. So what would be pros and cons of using array cluster and MLOps tools like Kubeflow, for example, instead of using Kubernetes cluster? Does actually array integrate with Kubeflow?
You can use Kubeflow to orchestrate array jobs.
Okay.
Now the point is, instead of using bare metal cluster Kubernetes or a vanilla Kubernetes cluster, the thing is, array will offer you a layer of abstractions that you don't need to take care of. If you want to run Python function distributed across multiple pods and so on, you'd have to develop this yourself using whatever tools you might be using. But Ray helps you focus only on the Python function and not take care of using the distributed programming, and then collect all the values and then make sure that you are handling all the possible errors. If one node dies, how will you handle this and so on.
So Ray uses Kubernetes as the computing engine, so to say. As a
it can be running on Kubernetes, but it also can be running on
ECS,
your hardware.
Or you can install, like, you can physically just, I don't know, get some nodes and then put the agents there, right? And then Ray will run there.
Yeah.
Do you know if there are any advantages of using like plain Ray versus Kubernetes Ray? Like less overhead, I guess?
I've tried both, and using Ray plainly on hardware is much easier to get it up and running. Before with Kubernetes, there is this kuberay operator that helps you run Ray on Kubernetes, but there are a lot of rough edges still, and it's not really well integrated.
Yeah, so what about CPUs? So you spoke about GPUs, but there are also big machines with, like, I don't know, tens of CPUs, sometimes even thousands of CPUs. Can Ray still be useful for them?
Yes, you can use Ray to basically distribute resources across multiple processes, and also Ray will be able to work and run on these cores.
And in the example you showed, can we say, okay, like this task requires, I don't know, 1 GPU?
Yes, it would be something like this here.
We don't see, but I imagine that in the decorator, you can see.
Yeah, in the remote decorator, you can specify how many of GPUs do you want. We will see it in the demo as well.
Yeah, what about boosting trees like LGBM, LightGBM or XGBoost?
Yeah, Ray has a very good integration with XGBoost. I don't know about LightGBM, but I assume it should be integrated. And then Ray would make sure to run this workload in a distributed way in your compute power as a whole.
Yeah, well, we covered the questions. Let's see the demo. Thanks for answering.
No worries. I'll try and share the screen again. Okay.
So the font is tiny. Can you enlarge it?
Yes. Perfect.
Yeah, that's better.
This one. Cool. So what I have here is the Ray UI. I have created a cluster with 2 GPUs. Here we can see. Right now I have only 1 node. Later, if we have time, I will try to add another node in the cluster, and then we can see how.
GC means Google Cloud, right?
GC means Genesis Cloud is one.
Genesis Cloud. Oh, sorry. Yeah. They are based in Munich, right?
Yes, Genesis Cloud is based in Munich. It's one GPU hardware provider. It's a cloud provider, but focused on GPUs. They're really good, and I'd encourage everyone to check them out. And here I've prepared a demo, one Jupyter notebook where we'll see.
Maybe you can make it a bit larger. Still tiny.
Sorry.
Yeah, that's good.
I hope it's better now.
It's way better.
Cool.
Yeah.
Perfect. So if we start, basically to get started, we just need to import Ray and Ray init. That's all you need to do in order to have your workloads be runnable in the cluster. Now we can see here that we have this Python version installed, we have Ray version, and then a link to the dashboard. The dashboard is this what we saw just before. And regarding the question that you mentioned in the beginning, can we define how many resources do we want? We definitely can define this in the decorator. In this case, I'm using 2 GPUs. And if I were to run this function, then we can see initially we get a reference, but then eventually we get the value. What I'm printing here are the IDs of the GPUs. And here I have 2 IDs, 0 and 1. But of course,
how does it actually work? Because like this function is executed on some node, remote node.
Yes.
And then when it is executed, it prints something to standard output. And then all the standard output is sent back to the, I don't know, like the driver of this notebook?
Yes, it goes back to the driver, and then that's what we can
It's also called driver, because I am using like Spark vocabulary.
Yes, indeed, it's called driver. And here, if we check the task table here, we can see that one task was executed in the Ray UI. And to do something a bit more complicated, we'll try to sum 2 NumPy arrays. Here we are defining the function, and then just as an example here, instead of creating some complicated arrays, I'm just creating 1 array of ones. And what I'm doing now is creating array 1 with ones, array 2 with ones, and then I'll try to sum these 2 arrays up and see what happens. Now, as you saw, the function returned very fast, but if I check the type of the variable sum, here is just an object reference. This is a future that Ray returns to me, and now if I want to get the value of sum, I can execute this ray.get. Oops, something happened. And then here I can now get the value of the sum. The problem here with ray.get is that it's blocking. So every time I run ray.get, I need to finish all the instructions that I've given to the cluster and then get the value. But this is not necessarily what I need always. I would like to start multiple jobs, let them run in the cluster, all are scheduled independently, and then I get something back from the cluster. And that's it. That's all you need in order to run a task in Ray. Now I've prepared a short script about how to train MNIST. Just some normal data set, some quick start data set, and then how to run it in Ray. If you check, the code is very similar to what you do to run a PyTorch, to run training with PyTorch for MNIST. Here I'm loading the data, training and test data.
Why do you need a lock there?
The lock is basically to tell Ray that I'm downloading this data and these are being used right now.
Mm-hmm. Like what happens if I don't add this lock?
Probably multiple threads will start downloading them and they may start overwriting the data from one another.
So it can actually occur that this function is executed by multiple nodes, right?
It can be. In distributed computing, a lot of weird things.
Like multiple threads on the same node, right? If it's different nodes, then it's fine, because like then each node would have its own copy of the data. It's fine.
Yeah, but basically, if you check in the architecture diagram, each worker is a separate process. So basically, each CPU is assigned to a worker, and then you can have multiple workers running in the same node, and then might happen that one node is not responding, and then it gets assigned. The task gets assigned to another worker, and then funny things start happening. And now we define the model, the neural network it's a bit hard to see here because the font is big, but if you want, all the code is on GitHub, and I think there is the link provided to the GitHub repo. And then we just have the training function. What you can see here is that we have, instead of using the normal torch library, we are using ray.train.torch. And if we check the imports here at the top, we can see that we have some things that are imported from Ray in order to make sure that training can run in a distributed way and can run in the Ray cluster. And then, right, this is fine, but then here, towards the end, we have the train fetch amnest function. Here we define the workers that we want to use, and then we have this scaling config that basically tells Ray that I will be using this amount of workers and I want to be using GPUs. If I specify here that I want to be using GPUs, and then I define one trainer, which is, in this case, it's going to be a torch trainer with the scaling config, with the train config, and the function that will be used for the training. And then just trainer.fit, and then I'll be getting the results. So I'll be running this function initially with one worker, and then we'll see how this moves or how the performance improves if we were to use two workers. And nope, of course. Yep. Now I can see that the training process is started, and here I'll be starting to get some logs. Here we can see that we are using one out of the two GPUs that we have available. And now in our cluster, we can see that in the UI, let me try to make this a bit smaller. In the cluster, we will start seeing that the GPU is being used. And of course, if we go in the task list, we will see some tasks that are related to this job. Here we will see some executing some torch training. I think we should also see the worker here, the torch trainer worker, which is dead, and means that the training has finished. See, now the job ran for 1 minute and 2 seconds, and then finished. Here we have some results, and with some 84% accuracy. Now, if we were to run the same job with 2 workers, we should say that it will ideally take less. It will not take half of the previous time, because whenever you do distributed processing, you have some overhead introduced between machines. But we can see that now we are using both GPUs that we have available. And then we see that the training is running now. I've only put 3 epochs just for not to have everyone wait here. But we should be able to see that in the cluster, both our GPUs are being used at the same time. So we see that this time it took only 47 seconds to do the training. Of course, not every time you want to run a training workload, you will be running it from the Jupyter notebook. Therefore, you can use from the terminal or from whatever instruction, from whatever orchestrator you're using. You can use ray submit job command, and then this will take care of running the job in the Kubernetes cluster. If you were to put it on a terminal, I hope the font is visible here.
Yeah, it is. Yeah, thanks.
The command would be looking something like this. Basically, ray job submit, and then you define some more instructions about the workload that you want to be running. Let me first stop the kernel, interrupt kernel. And so now if I were to run this job from the terminal, we can see that also in the cluster, a new job will appear. Here is ray submit job, and it is basically the same code that it was run previously, and now I just specified that I want to be using 2 GPUs. And here in the cluster, we should be seeing the GPUs being used fully. And also we see the logs here, but we can also check the logs in the job itself. And you can follow up everything that is going on with the cluster. Yeah, Alexei, you wanted to say something?
Yeah, it looks quite impressive. So I wanted to ask some questions. So unless it's time, it's good. Like unless you want to add something.
What I wanted to show is how to add new instances in Ray.
Yeah, that's interesting.
So now in the other window, I have prepared a separate instance in video SNI. Here we can see that we have 2 available GPUs in this instance. And let's see how easy it would be to add this other instance in the cluster. Resume share, sorry. I have this command prepared in my other window, and basically all you need to do is say ray start and then specify the address.
And how easy it is to install Ray? What you put on this machine?
It is relatively easy.
Is it like apt-get install Ray, or
it's pip install Ray, but you need to have
pip
a few
install
dependencies. Yeah.
Like probably you have to have like this CUDA, right, and like all the NVIDIA stuff.
CUDA driver and all the other stuff needed. You need to have them upfront, but the rest is relatively easy. There is a lot of documentation online about it. And now we can see that we have 2 nodes here in the cluster, and each of the nodes has 2 available GPUs.
So let's say if we want to scale a cluster like automatically when we have more workload, would something would just request new nodes from, I don't know, LWS or Genesis Cloud or whatever, and then this node would already have this instance would already have, like, I don't know, Ray on all the dependencies installed, and then on the startup, when everything is ready, it would automatically execute this command, right? Ray add to the cluster.
Yeah, this would be one way. In practice, you'd use the Ray autoscaler. You just need to tell how, if you're using something that is not very common, how can autoscaler get a node up and running. And then you'd usually just prepare an image for this node and then provide a few commands that will create the node.
See, that's cool.
For instance, we can check now, for example, init is, okay. Let's try and restart the cluster. Okay. So now if we were to ask for 4 GPUs, then we should be able to get yeah. No, sorry, wrong. Basically, yeah, the truth is, if we have one node, each node has 2 GPUs, so we cannot request for one task 4 GPUs. It's just each of the hardware available can only provide 2 GPUs. So in order to run one task, this task needs to run in one machine. Therefore, you can only use up to 2 GPUs here.
So we need also to think how exactly we want to, like, let's say if we have a job that needs to be run across multiple nodes, then we need to think like how exactly we write our functions. Like maybe we should have. Yeah, sorry.
So in Spark, you'll do this with partitions, and in Ray, you can do something similar. So make sure that
right.
Each task has enough hardware available.
Interesting.
That's actually all from my side. I wanted to do a short summary, but we can do this after we answer the questions.
One of the questions I have is how difficult it is to have a Ray cluster up and running. You mentioned we compared when I asked you about Kubernetes, you said like using plain Ray is way easier than Kubernetes, but still like, let's say if right now I want to start to have a Ray cluster, how much time will I need? Is it a day? Is it an hour? Is it like?
I think it's in the range of hour. So if we check here, I'm just trying to document all the steps that I used to have the Ray up and running. What you need is to have Python installed in your machine and also pip installed. These are really standard instructions that you would need, but installing the dependencies about Ray is only these many packages that you have to have installed. And then once you have everything up installed, then you can just run something like Ray start -- head. This tells Ray that the node you are starting is gonna act as head of the cluster, and then that's it basically.
That's relatively straightforward, right? So probably there are some, like when you try doing this, there could be some details, but when you do it once, then the next time is probably very smooth.
Indeed. And then you saw how easy it is to add a node to the cluster. It is relatively easy, but the devil is in the details. Once you need something specific, might become more complicated.
So first questions and then summary, right? So because there are more questions. Question from Max: if there is any way to integrate Ray with Kubernetes, and I think you answered that there is a way to integrate, but then the question continues: if there are any resources for that. And you started answering this question, I think.
I think Ray is the answer to the question. There is a lot of tooling and people around this community, so you can check this out. Also, Ray, the Anyscale team is very responsive in the Slack channel. So you can join the Slack channel of any skill, and I'm pretty sure you'll be able to get your questions answered.
Yeah, thanks. Does Ray support model parallelism? I don't know. Do you want me to share the screen if it's easier for you?
Yeah,
with questions?
probably. I don't need to.
Does Ray support model parallelism besides data parallelism for large PyTorch models like LLMs? Because what we saw was more like data parallelism, right?
Yeah. Ray does support it. To my knowledge, also ChatGPT was trained with Ray, but I've not been this deep into Ray for model parallelism yet.
Okay. So when you are, then you'll do another workshop, another demo, right?
For sure.
Another question from Taras. Is the following true? On the specific written functions, tasks, methods can benefit from Ray. That's why Ray trained PyTorch is used and not Ray remote.
So it's difficult to say yes or no. The truth is, there are diminishing returns when you are doing parallelization. Therefore, you need to be careful in a lot of aspects of the code. The ray.remote decorator just tells Ray that this particular function will be running in the cluster. While Ray train PyTorch is used to make sure that your PyTorch code can run in the Ray cluster in a good way. I'm not sure if this answers the question.
So I might be completely wrong, but from what I saw in other frameworks, so these specialized functions like Ray PyTorch or like in other frameworks, they might use, so instead of you implementing this, for example, model parallelism, this Ray PyTorch can already implement that and you just use it. Right? So that there could be some, you cut corners instead of implementing all the distributed, like all the way specific frameworks handle distributed trainings. You just rely on what the Ray team already wrote and you just use it. Otherwise, you can write it yourself using just Ray remote. But why if it's already written? Or if you want to have more control over what exactly is happening on the
Yeah, if you need something very specific.
Let me check the live chat if there is anything. Yeah, nice, love it. That's awesome. Yeah. No questions.
Nice, great. Okay.
Yeah, that was indeed awesome. I really liked the presentation. Like, it looked so simple, so I think, like, my suspicion is like there must be a catch. Like, why it's so simple? But hopefully there is none, and it's just.
Yeah. Just to recap, basically, distributed computing is a necessity. Ray helps us make distributed computing simple. But there is a lot of work to do still there, and to make sure that your use cases work. I think it's also not just a walk in the park, although that's the vision for Ray. Nonetheless, it can help you a lot to scale machine learning workloads, especially with Ray Air. And you can use Ray as you want also to build your own apps and libraries on top of it. Yeah, also from my side, thank you so much. If you want to stay in touch, feel free to shoot me an email or connect on LinkedIn.
Yeah, thanks for joining us for, is it second time or already third?
It's second time.
Second time. Okay. Well, I am looking forward to inviting you again. So whenever you have topics, they are always awesome. So I'm sure maybe you will think, okay, like, oh, there's this cool new framework and what I want to do a presentation about that. So do not hesitate to reach out again, and we will make it happen. So thanks again for joining us and sharing this knowledge with us. And thanks everyone for joining too and asking questions and being active. And yeah, I don't know what else to say apart from enjoy the rest of your day.
Thanks for having me. Thanks everyone.